The cosmos is filled with endpoints we think we understand. When a star exhausts its fuel, the laws of physics usually dictate a predictable final resting state. Traditionally, stellar death has been viewed as a strict binary. Lower mass stars collapse into white dwarfs, dense, glowing embers roughly the size of Earth. Heavier stars cave in on themselves to form neutron stars, objects with the mass of a sun packed into a sphere no larger than a city. Between those two extreme states lies a massive gap in our observations. While we have mapped the endpoints, the transitional stages connecting them have historically gone undocumented. That gap closed in April 2026. Astronomer Nathaniel Faxon Cherier published data on a celestial object designated Gandalf, with physical properties that fall outside the parameters of both known endpoints. Finding a star that exists between these two defined states suggests that stellar death isn't always a binary outcome, but a spectrum with its own unique intermediate stages. To understand why Gandalf challenged our models, we have to look at its physical dimensions. Telescopic observations revealed an object with a contradictory set of traits. This represents Gandalf's mass. At 1.02 solar masses, it contains the entire weight of our Sun. But that solar mass is squeezed into a radius of just 0.018 solar radii. This puts its physical size at roughly the same diameter as our Moon. When Cherier's team analyzed the light coming from this object, they found distinct spectroscopic signatures. The reading showed strong hydrogen alpha and beta emission lines, along with traces of helium. These specific emission lines are driven by intense magnetic activity. They reveal an atmosphere governed by a magnetic field measuring between 1 billion and 10 billion Gauss. If you try to classify Gandalf as a white dwarf, the math fails. It is far too heavy, and its magnetic field is thousands of times stronger than what you find in a typical white dwarf. Try to label it a neutron star, and the metrics fail again. Gandalf's physical radius is much too wide, and its magnetic field is significantly weaker than that of a typical pulsar. It exists exactly in the middle. These conflicting measurements prove Gandalf represents a distinct class of stellar object, and we need to determine how it actually functions. To figure out what Gandalf is, we need to see its future. Astrophysicists use the MESA stellar evolution code to digitally fast-forward a star's lifespan based on its observed physics. Tracking the baseline at year 0, we plug in Gandalf's parameters, a 2,159-kilometer radius, initial density, and 1 billion Gauss magnetic field. Advancing to 10,000 years, severe contraction drops the radius 10%. By 100,000 years, a density spike triggers neutronization. Neutronization happens when gravitational crushing forces become so immense that electrons and protons are shoved together, merging to create pure neutrons. At the 1 million year mark, as the star continues to shrink, its magnetic field winds up and intensifies, reaching 10 billion Gauss. Tracing this physical evolution shows that Gandalf is not a static anomaly. We're witnessing an active, violent transition captured in real time. The rapid contraction finally stabilizes at the 10 million year mark. On the final dashboard, the radius locks in between 10 and 15 kilometers. The magnetic field peaks at 1 trillion Gauss, and the core has transformed into stable neutron degenerate matter. This 10 million year model provides a clear blueprint. We can now see how an intermediate object like Gandalf physically matures into a neutron star. This data has allowed researchers to officially classify Gandalf as a new type of object, the Semineutron Star. The existence of a semineutron star proves that stellar death can be a millions of years long journey rather than an instantaneous collapse. The next step is to hunt for more of them. By conducting new spectroscopic and photometric sweeps, researchers hope to locate other semineutron stars currently hiding in our archives. At the same time, teams will run thousands of varied MESA simulations, adjusting the initial parameters to map out the complete boundaries of this transitional state. Gandalf provides the direct evidence needed to connect these two phases of a star's life. To stay updated as we uncover more of these cosmic mysteries, return to MDU, hit the like button, and subscribe.